Hi folks. Today we're finally going to put together the idea of finding area or an integral, net area, and doing all this antiderivative stuff. So the fundamental theorem of calculus is this. If f of x is a function that's continuous over some interval from a to b, and we want to find the integral, like the exact net area, and remembering that area below the x-axis is counted negatively, then this is how it works. The definite integral, okay, which is that thing we're looking for, is just the antiderivative of the outer boundary or the upper boundary minus the antiderivative of the lower boundary. Okay, so these things all have something to do with each other. And the derivative of the antiderivative just gets you back to the original function. So it turns out that differential calculus and integral calculus, finding slope and finding area, are just two sides of the same coin. That's kind of the fundamental punchline of calculus. Sometimes people write this f of b minus f of a thing as big F of x just from a to b. So let's actually find some of these integrals. Down here we've got the integral from 3 to 5 of 2x minus 4. I mean, if I imagined that function, that's a line with a positive slope, and we're looking basically from the integral from 3 to 5. That's one that you could do with a trapezoid if you wanted to find out what the actual area is. But integration will get us there too. So here are the steps. We're going to find the antiderivative. Okay, so the antiderivative of 2x would be x squared. The antiderivative of negative 4 would be 4x. We don't need a plus c or a constant of integration here because it would just get subtracted off. And we're going to do that from 3 to 5. Okay, so right here, this thing in the brackets is our antiderivative, big F of x. Now what we're going to do is sub in the number 5 into that antiderivative. So it'll be 5 squared minus 4 times 5. Okay, that is big F of 5 minus the antiderivative at 3. Okay, so that would be 3 squared minus 4 times 3. We're just subtracting those two things off. We'll carefully work this through. So 25 minus 20 would be 5. 9 minus 12 would be negative 3. And the value of this integral will just be 8. So 5 minus negative 3 is 8. You could check that out geometrically. You're going to find the same result. And this is a nice one because it's a linear. We could find that area using some formula that we know. On the other hand, if we have a function like e to the 2x, which we know looks like this, and we're looking from the area basically from 3 to 6, okay, well, then it's going to be harder to use a formula. So we have to use this technique, this fundamental theorem of calculus. So first thing we do is anti-differentiate. So e to the 2x from 3 to 6. Now, let me just check. Is that really the antiderivative of e to the 2x? If I differentiate this just to check, I'd get e to the 2x times 2. Oh no, that's too big by a factor of 2. So I'm going to have to put a half in front here so that I get the correct antiderivative, the thing that differentiates back to e to the 2x. Once I have that correct antiderivative, all I need to do is sub in. Okay, so there's the antiderivative. We're going to sub in 6 and 3, and it's always going to be the antiderivative of that upper boundary, the one that's up top here, minus the antiderivative of the lower boundary. Okay. So that would be 1/2 e to the 2 times 6, which maybe you just want to call 12 right away, and 1/2 e to the 2 times 3. Or 1/2 e to the 12 minus 1/2 e to the 6. If you really want to factor this, you can. If you want to get a decimal approximation, you can. Those are all reasonable things to do. But there's an exact version of the answer. So factored, you could take out the half, you could take out e to the 6, but you'd still be left with not 6, but e to the 6 minus 1. Now, once again, I am dangerously doing this without an answer key, so hopefully I haven't made any goofs here. If I do, yell at the projector. It'll feel good. Okay. So let's just do a little more practice on some of these. And maybe you want to pause and try this on your own. You probably know at this point that if we have a power of a half, well, we want to write it as, if we have a square root, we want to write it as a power of a half. So now we can anti-differentiate. Power goes up by 1. Flip of the new power goes in front. And this is from 1 to 9. So what I'm going to do is sub in that 9 and sub in that 1. Now, you can use your calculator if you want, but we should know what a power of 3 over 2 does. Okay, so we'll have 2/3 as a coefficient here, sort of thing. 9 to the 3 over 2 means square root it and cube it. So the square root of 9 is 3, cubed is 27. Mercifully, 1 to any power is just 1. So what do we get? We get 54 over 3 minus 2/3, or 52 over 3. So that's telling us that if you had this square root function from 1 to 9, that's all above the x-axis, this area would be 52/3. Similarly, if we have questions where stuff is written in form that is not easy to integrate well or anti-differentiate, we'll just write it in a better form. So this is 4 times x to the minus 3 minus 1 times x to the minus 2. So there it is rewritten. And now we can anti-differentiate. The power goes up by 1, and the 4 stays because it's a coefficient. The flip of the new power goes in front. Maybe I need a little more space here. So let's zoom in. The 4 stays. The power goes up by 1. So if I'm at -3, it'll go up to -2. And then the flip of the new power goes in front. That's -1/2. Same thing with the other one. I'm going to have the power go up by 1, and the flip of the new power go in front. Well, the flip of -1 is just -1. And we're going from 1 to 4. Now, I probably want to clean that up. So that would be -2 x to the minus 2 plus x to the minus 1. You can use it from that form. Works great. If you feel like you don't like it like this, then write it as -2 x squared, okay, and then plus 1 over x. And we certainly can check that this differentiates us back to the original function. So it would be positive 4x to the minus 3. Yep, that's good. Okay. And the other one would give us negative x to the minus 2. Yep, that's good. So we're finally in a position here where we can actually sub in and see what happens. Let's put in 4. You'd have -2 over 4 squared. 4 squared plus 1 over 4. That's big F of 4 minus big F of 1. Okay, so that's -2 over 1 squared plus 1 over 1. And now we may have to do some shenanigans just with fractions. So at this point, it's really just arithmetic that we're dealing with. It's -2 over 16 plus 1/4 minus -2 plus 1, okay, or that's -1/8 plus 2/8, okay, minus this whole thing here would be -1, so minus -1. And we could write that as 1 plus 1/8. We could write it as 1 1/8. We could write it as 9 over 8. We could write it as 1.125. Any of those things are appropriate. So again, the main thing in here is that we anti-differentiate and then we sub in. One more that involves trig. So when we have trig, we think wheel of trig. And so the antiderivative of cosine is sine. So we'd have sine x from pi and pi over 4. And again, just sub in. That's sine of pi minus the sine of pi over 4. Well, let's see. The sine of pi would just be 0. The sine of pi over 4 is root 2 over 2. Okay. So this whole integral should be negative root 2 over 2. Or if you've learned that one as negative 1 over root 2, that's fine as well. You can write it that way. See, does that make any sense? Let's think about cosine. Cosine looks like this. Here's pi. Here's pi over 4. Okay. Here's the region we're talking about. And you can see that there's more area below the x-axis than above the x-axis. So that must mean that the overall integral should be negative. And that's what we found. Moving on, we can do some of these sort of in context. So instead of having the question set up for us, we could ask ourselves, what is the area under one arch of sine 2x? Well, let's just draw that. Sine 2x looks like this. Okay. If it were sine x, it would have a period of 2 pi. This has a horizontal stretch by a factor of a half, or we could say it has a period of 2 pi over 2, or just pi. What is this area? Well, it is the integral from 0 to pi over 2 on sine 2x. Okay, and it's the area with respect to the x-axis, so hence the dx. There are other places you could find this arch, like it recurs infinitely many times, but this is the easiest one because it's the closest to the origin. Okay, so we'll do our regular stuff here. We'll just anti-differentiate. Okay, so I need wheel of trig. Sine differentiates to cosine, differentiates to negative sine, differentiates to negative cosine. Okay, so sine differentiates, anti-differentiates to negative cosine of 2x. I think that's my antiderivative. Let's just make sure that it works out. We'll check by differentiating. We differentiate negative cosine, it'll turn into sine of 2x. When we differentiate to check, oh no, we'll get the chain rule. We'll get a times 2. So it would get us 2 sine 2x. We just want it to be 1 sine 2x. So we need to fix it up with a little coefficient. So a good way to anti-differentiate is to take your best guess and then see if you can improve it. And now let's just work this through. So negative a half cosine of 2 by pi over 2, 2 times pi over 2, minus negative a half the cosine of 2 times 0, colloquially known as 0. So this is negative a half times the cosine of 2 times pi over 2. That's just pi. Minus negative a half times the cosine of 0. And we could sub this in our calculators. But the cosine of pi is way back here. It's negative 1. So this would be negative a half times negative 1 minus negative a half. The cosine of 0 is positive 1. Oh, that's a lot of brackets. Let's see what happens here. Negative 1 times a half times negative a half times negative 1 is a half. Okay, plus a half. Oh my gosh. We get an area. And notice in this question, it did ask us specifically for an area. That's why we're giving an answer as area. We got an area of 1. I think that that's bananas. Look at the amount of crazy work that we did in here. We had pi, a transcendental number involved. We had a trig function. We had a weird shape, a cyclical shape that's always repeating. And after all that, we get this amazing answer of just the simplest number we could imagine, just 1. Anyways, food for thought, I guess. How does this happen? It happens through the magic of the fundamental theorem of calculus. Okay, a couple of other things. We could also be asked to find a boundary. So we've got this situation here where we've got a function y equals 2x. We're saying the area between 3 and something, essentially, is going to be 4. Okay. Let's find out what k is, and k is greater than 0. So we'll just go through our regular stuff. Okay, so the antiderivative of 2x is x squared. The boundaries are 3 and k. And we can just sub in the same as we normally would. So that would be k squared minus 3 squared. That's not helpful. We can't solve. But the thing is, we know that the value of this integral is 4. So whenever we do all this stuff, we should get 4. So this is equal to 4. So let's set it equal to 4 again. Our unknown just happens to be in a different place here. So in other words, k squared minus 9 is 14, or k squared is 13, or k is, well, normally plus or minus root 13. But since k is positive, we must say that k is just positive root 13. So if you're looking for a boundary, all we need to do is go ahead and set up the equation, do our regular stuff, but we'll have an unknown in a different place. One last one. We're going to do the same sort of idea. We've got one of these butterfly-looking things, and it's saying the integral from a to 5, this area is just 1. Find a to 3 sig figs. So we'll do the same sort of thing here. We've got the indefinite integral. I'm careful here. The definite integral, when we're doing this, involves finding the antiderivative. Okay. So that would be ln absolute value of x. The absolute value doesn't really matter, okay, because we're going to have positive numbers. We're saying that this integral is equal to 1. In other words, ln 5 minus ln a equals 1. Now we need to isolate ln a. So we could put the ln 5 on the other side. So negative ln a equals 1 minus ln 5. Okay. Or we could just go to our calculator at this point. And it's going to take me a second to find it. Calculator. 1 minus ln 5 is negative 0.609. So negative ln a is negative 0.609, or ln a is 0.609. And we've still got a problem here. We've got to figure out what a is, not just ln a. And the way we figure that out is by saying, oh my gosh, we have to go to exponential form. We're talking about a base of e, we're talking about an answer in exponential form of a, and we're talking about an exponent of 0.609. So in exponential form, this reads as e to the 0.609 equals a. And we can go ahead and get the calculator to work that out. So e to the power of that answer that I just grabbed, but positive, so I'll write it in again, 0.609. I could have more decimal places. Okay. Gives me 1.84. A is 1.84. If you have a really fancy calculator, you can check this out. So in this calculator, I can get it to do definite integrals. And I can just say 1.84 to 5 on 1 over x dx. And hopefully that'll give me 1. It gives me really close to 1 because there's some sort of rounding that's happening. If you have a fancy calculator, you can do that to check, but I need to see process. And if you're stuck between whether to just write a correct answer with no work or good work and maybe an incorrect answer, you will get more marks for incorrect answer with good process. So what do we do to do some practice on this? Well, further in this integration handout, there is some definite integral practice. Okay, this says Math 611B, definite integrals. I would do A, B, C, maybe F on this one, maybe D as well. And just pick away at a few of them. If you want to do more, you can. I think probably the main goal at this point, though, will be getting ready for your Chapter 5 test tomorrow. So with the remainder of the time, you do a few definite integrals, and then maybe take a look at some practice for that Chapter 5 test that is going to involve stuff from the first and second assignment. So that means there's going to be some graphing, some max-min, some optimization, some related rates, and some Newton's method. Take care, folks, and have a great day.